of disease models where circuit diseases have been suggested in some of those entities. These are our dreams. Of course, it's still quite some work to do, but all of this requires much better reconstruction, and this is why we are currently focusing on that. Thanks to the people involved, the retina team back in Heidelberg, and then my team in Munich for the cortex work, and thanks to you for your attention.
Sorry that you had to rush through the data. If there is a question to Maurice before we have to get to me. If not, then again, he and Marcel will be here till tomorrow noontime. Feel free to approach us to ask more questions.
Thanks.
Thank you.
Sure. Oh, oops. Just have to switch it off. So I think. So in the retina, we played a bit with it. It's a little difficult in the retina because it's a very shallow network. Therefore, shallow, I mean, it's essentially bipolar cells, African cells, Chinese cells. So it's three, maximum three layers, and that makes or it's yeah, well, it's just not very diffuse. It's not very diffuse. It doesn't have that level of high order. So that's why I think those and that's actually my interpretation why the direct application of these methods was not so successful. So essentially, in special mode, can we use some of these methods to find something? And that worked roughly okay for the large classes like bipolar, African cells, but sometimes
Most most of them believe that they are really bad at memory because people keep telling them it might affect memory and might problems with memory, but they really believe that they are really bad. So they do psychological tests with ego as a controlling factor. You shouldn't tell them they suffer because they believe they are bad, but it's actually from ego.
Okay, good afternoon, folks. Time is short, and I want to have the students present their stuff today. So I just want to give a sort of an intro to what we're going to hear about today. And it's not going to take very long. Well, that's not. We're going to tackle three questions. If you remember last time, we had sort of a quick overview of what's going on beyond V1. And I mentioned a few things which we are going to touch on and elaborate on today. So the first is this issue of the buildup of receptor field complexity. And I've given you sort of an example here from a sketch we've had in which what you can see is that as you're moving up along the hierarchy, receptor fields become bigger and they become more complex. And lo and behold, finally you get to these neurons that you find in infratemporal cortex, which are now sensitive to faces or to very complicated objects. And the first question we want to deal with is in terms of basically receptor field structure. I think you've heard from Shaul the famous example of simple cells and complex cells, and how do you generate a simple cell, presumably from the input from the LGN, and probably the issue of the cross connectivity within V1 shaping the receptor fields in simple cell receptor fields, and the next stage, complex cells. And now we want to understand this in more sort of, it's increasing complexity here when you're talking about much more complex receptor fields. I mentioned in a few words in the last talk, Tanaka's sort of simplifying hypothesis in which he was trying to find out what are the basic alphabet, if you want, elements of alphabet, visual alphabet that you can find in posterior infratemporal cortex. But we thought, we sort of thought about together about the caveats of this sort of approach, and basically it seemed to be somewhat arbitrary, and one was wondering if you were to start from a different simplifying direction, would you get to the same final stage in terms of the basic receptor field properties if you were to choose a different branch on the tree? And the one thing that we came up with was, well, maybe one needs a sort of a theory to think about what would be the optimal way to build a receptor field. And the first talk we're going to hear is going to be about such an idea, stemming from basically from information theory from Shimon Ullman and his group, in which they specifically looked at faces and face cells and asked themselves, okay, what could be the optimal building blocks to generate a face selective neuron in IT for the purpose of face categorization, saying, is this a face or is this not a face? So that's going to be the first task we're going to tackle. And then we're going to move into the issue of representation. And we're going to hear about what is the relevant coding scheme for object representation. Is this, so I mentioned this, should we look at this as a distributed coding? Is this domain specificity? Is this sparse coding, or is this distributed in the sense that is shown here, that most neurons fire for many sorts of stimuli, and it's really the pattern in which you can distinguish between stimulus A and stimulus B. And this is going to also touch on another question, and that is there a similar code of representation across species and across spatial scales? And for that purpose, we're going to compare representations, distributed representations that are based on neurons, single neurons, or multiple single neurons, versus a code which is based on voxels. And as I mentioned briefly last time, voxels are the activation level of a voxel is a grand average of an order of 1 million neurons. Okay, so you're looking at a much at a completely different spatial scale, and also in terms of timing, the activation of voxels are you sum them, and the temporal resolution is about I would say of the order of a second. Okay, so we're talking about again a factor of 3 in terms of the timing issues. And finally, so in order to touch on that, we're going to talk about a comparison between, as I said, a representation, distributed representation based on evidence found from monkeys, single unit recordings, and humans, in which the important thing is that the evidence is from viewing the same images. Okay, so you can make a direct comparison because we're talking about the same representation of the same images. And finally, we'd like to discuss the issue of objects' constancy. So as I said, one of the main features of the visual system is this ability to extract a category or an exemplar of a category which is immune to changes that can be due to changes in lightness or position or viewing point, shading, etc., etc. And this is sort of a mystery of how can this be achieved. So we're going to, in the third talk by Hagai, we're going to discuss. Did I say that you were second? We can switch this. I mean, there's. Okay, so we can switch the two. I mean, both are dealing with distributed representation. If I mentioned to, you're right that before the talk I said you'll be second. So you'll go second. Describe this in terms of sort of and serve as a primer for the third representation. So we're going to swap these. Sorry about that. Okay, so let's start with the first talk by Lily, in which she's going to address this issue of phase cells and their receptor field properties, and how can you establish such receptor field characteristics from the building blocks of neurons which are sensitive to objects, to edges, and what should be the optimal building blocks for such a representation. Yeah, you can, whatever. You can use my computer. You can use whatever you feel more comfortable. Maybe the big one would be whatever. This one's at the moment. This one it's connected to my computer. Would you like?
Okay. I have it also on Dan's computer.
Let's go. Okay. So you want to bring Dan's computer? Whatever you feel more comfortable. I mean, let's just
use this because you're already here, right? So may I?
Absolutely. I was just thinking that the mouse would be a little.
I have a plug.
Go for it.
Okay, I see. The mouse doesn't work. Okay. So, hello everyone. Good morning. So let's look at this picture, and who can tell me if there's face or no face in this picture? There's a face, a human face. No, are you sure? Okay, so no face. What about this picture? Is there a face or no face? There's face. Great. And how many are there? 4.5. Okay, so you know this because you're human, but what can computers know today? So in 2014, if you put this image into Facebook or any other face recognition software, it'll automatically tell you these are the areas where you have faces. And that's called classification, as Udi mentioned. But not only that, Facebook will also recognize who it is. It'll say, hey, is this your friend, Joe Smith? We know him. And this is called recognition because we want in the end to know who it is. We want that information. So in the particular paper that I'm presenting by Ullman et al. At Weizmann, they focus specifically on the first component, so on the classification part. And they asked the question, how can a computer tell if there is a face in the picture or not? And part of their work is that it was done in 2002, so notice this was about a decade ago when all this technology really took off. So what's the history of face recognition? Well, it really started in 1960 with the first semi-automated system, and they focused on recognition. The idea is that humans would do the classification part. Humans would say, this is a face, there's an eye, there's an eye, there's a mouth, and then the computer would calculate a ratio and then compare it to a face in the existing database and say whether or not it's the same face. So the computer did the recognition aspect. They did this semi-automated system for about 30 years, and it wasn't until late 1980s that somebody started applying principal component analysis to face recognition. It might sound very complicated, but it's actually very simple. You take a main image, and you say this main image can be represented by a linear combination of sub-images. So it's essentially linear algebra. Instead of numbers, you have images. And the first image on the top left has the most information. And as you go down the number of sub-images, you have less and less information. So essentially, you can get rid of many of the images on the bottom. And what you're left with is analogous to a basis pair or a basis set of all your sub-images. This is called the principal component. So what you have is your main image is a linear combination of these principal components. It's pretty cool because it applied what we learned in linear algebra to this analysis. So from then until now, there's been a lot of development in fancy principal component analysis, using different filters to find bases, wavelets, and Gabor functions. And it's used both in classification and recognition at this point. So what happened in 2002 with Ullman et al., the paper that we're talking about, is that they said, hey, we don't think our brain represents objects using sub-pictures. You know, we want a biologically relevant model. So this is where they decided to see what happens in the brain, how we represent the image, and if we can use that process computationally, and if that would be a more natural way to recognize and classify faces. So in the brain, biologically, as we've learned from Shaul and Uri, you get the visual stimulus into the retina to LGN, V1, V4, TO, and IT. And we know that at the first couple of stages, it represents very simple features like edges and receptive fields. In the later stages, and computationally, it does input reconstruction. It takes the light and transforms it into electrical signals. We know that later on, it represents moderately complex figures, and that eventually, in a higher level, it does partial and complete image representation. But computationally, it was unknown at that time. And they wanted to look at this and say, well, computationally, the brain probably extracts basic building blocks, fundamental features for object classification. So the question is, what are these features? So if we take away a lot of the extra information, we're left with the types of features are simple, moderate, partial, or complete. And let's group them together. And then they ask the question, as an example, this is a complete picture. This would be simple objects, so you can see it's like very small fragments of the full image. Some intermediate objects are, a little bit larger fragments, and partial and complete views would be even larger fragments. So that's what they mean by these building blocks. And they ask the question, which feature is most important for object classification? And they hypothesize that it's the moderately and partial face fragments. And they call these intermediate features. So the hypothesis is that intermediate features are most important for object classification. Are we all following here? Okay, so it gets more complicated because how do you prove this hypothesis, right? So they ask two questions. One is which type of feature yields the most information, and the other is which type of feature gives the most accurate classification. So for the first question, it turns out there's a mutual information or merit formula that's well established in computer science, which looks at two binary variables, one being the fragment of an image, and the other, C, being whether or not it is in a face. And the mutual information is the information conveyed by S about C. So if we see the fragment S in this image, how does that affect our certainty of whether or not this image is a face or not a face? So the entropy, so there's this equation, it's an entropy equation, and entropy essentially measures uncertainty. We can get into the math details if you like, but it's actually very simple. So entropy is a sum of the probability times the log of the probability, if you remember from calculus. In this case, they give you the probability based on the number of images in the training set. So the probability that it's an image is 0.05, and the probability that it's not an image is 0.95. And from there, you can just plug in and chug. What?
Probability of face.
Yes, probability of face image, yes. The idea here is that, the main idea here is that this HSC, the entropy of the class, is a constant. So it doesn't change. It remains the same for every image. And the main idea here is that the entropy of the class given the fragment F is a variable because it's the additional information provided by the fragment. So, and this is a variable and it's always less than H of C. So your value for mutual information or merit is always positive. And then it's a similar equation if you write it out, and all of these values can be found, these more complicated probability values, can be found using their exhaustive search function. So that basically take the fragment F across all images in their training set and determine if these fragments are, if the fragments are in F and if the image is in C. If the fragment is in the image and if the image is in the class. And then they vary the size and resolution of the fragment because the face might be larger in some pictures and smaller in other pictures. So then they do a stepwise, I think by 3 pixels, they do a stepwise exhaustive search function to get these values. And essentially what they're left with is, so they take these 148 face images, they also look at cars, and they calculate the mutual merit for over 10,000 fragments. So here you have some examples of car fragments you see that they took. And then they ranked the mutual information of these fragments. So essentially, after finding the fragment with the highest mutual information, then they searched for the fragment that had the next highest amount of information. So here's a sample of what they found. The fragment that had the most mutual information is the part with the eyes and the hairline. So I guess usually when you see eyes, you think, okay, it's a face. And then you have the hairline with a mutual information of 0.18, and you have the nose. And essentially the way it goes is counterclockwise. So this is the one with the most mutual information. the next highest, next highest, next highest, next highest. And over here you can see this is interestingly just a picture of the whole face, but with very low resolution. And so that, when you see a low resolution with two eyes, something dark, then it gives a lot of information about the structure. Another interesting point is that the fragments cannot be represented by the subfragment. So if you have this fragment here and you say, well, I know a lot, is it enough just to have this eye? And the idea is no, it's not. You need the actual intermediate size. So once they have this, they can answer their first question. Which type of feature yields the most information? Well, it's intermediate fragments. It's in line with their hypothesis. And now they can ask the second question is, which type of feature gives the most accurate classification? So when you're classifying a picture, so say you have a picture here and you have your classification software. If there's a face and you say there's a face, then you're correct. If there's a face and you say there's no face, then it's a false negative. Now say your picture has no face and you say there is a face, then it's a false positive. And if there's no face and you say there's no face, then you're correct. So keeping this in mind, they developed this algorithm. This actually, I don't know where it's from. I think they just developed thought of something that was weight-based that made sense. And again, it's not very complicated. So what is max F? So F is the fragment. K is the type of fragment. So K is the columns here, the type of fragment. I is the number of fragment within each type K. And so within each column, they chose the best representative image that matches with the novel fragment that you're looking at. So that's the max function. Basically, within the column, they choose the one that has the maximum response to the image they're comparing to. And then for the threshold, it's they train this weight-based system with a training set of no faces, and the threshold is set to where all the false positives is 0 in a training set of no faces.
Do you know where the numbers WIK come from?
Yes. So WIK is the next one. W is the weight. So this is probably the most important part of this weight equation. And the weight is a logarithmic function of the likelihood ratio. So it's the likelihood ratio that S is found inside and outside of class C. So for example, if you have this segment, it is equally likely to be found in a face as it is likely to be found in a boat, because it's a very small segment. So the likelihood ratio would be quite close to 1 almost, right? So that would be your weight that you attribute for this particular fragment. Now if you had a larger fragment, then it's much more likely to be in the face and much less likely to be in the non-face, because it's very specific. So your likelihood ratio would be much higher. So that's what the ratio represents. And for each image, they sum up all these weights for each type of fragment. So hairline, nose area, eye area, and so on and so forth. And so if you look back at our first, the fragments that they found, you notice that the weight doesn't necessarily correlate with merit. So if a fragment has high merit, it doesn't mean that it has also high weight. It correlates, but it's not always exactly. So for example, this is 5.5 and that's 6.45, but they have the same merit. So they show this in a couple of graphs, and the square boxes represent merit, and the triangles represent weight, and they graph the weight and the merit relative to the object size. And what pops out is that the intermediate fragments always tend to have the highest weight and highest merit. So that's the main idea they want to convey, is that biologically, these intermediate fragments are the most useful building blocks that we have. So they use this weight formula to test 200 novel faces and non-faces. And if you remember here, you have the correct, false positive, false negative, and correct. So when they use all sizes of fragments, they get quite a good response, 97% correct and 2% false positive. And notice the rows sum up to 100, right? Because if you 97% face, then you know that 3% you labeled non-face. So they're correct. If they use only small fragments, so really small areas of the face, they get a very high correct ratio, but they also get a very high false positive. And this is what we said earlier about the likelihood ratio. If you have a small fragment, it's also likely that it's found in a non-face. If you have an intermediate fragment, you do well in both instances. So you have 96 and 0%. And if you have a large fragment, actually I should ask you what you guess it is. You have a very good false positive, as in you have no false positives, but you're less likely to see all the faces because each large fragment is so specific that it can't match to every face you have. So we can also take away the values here to make it easier to see the relationship. And here we see that intermediate fragments give you the best results when you're classifying images using this method. So here they just show you some examples of images where they found faces, and they show that they looked at different resolutions. So for example, in this resolution you see these two, but in a smaller resolution you see the larger face. And they show that some non-face images have facial features in them. Although I kind of don't see the facial features that they present, and that's about it. So with the second weight-based function, they're able to answer the question and say that intermediate fragments give the most accurate classification, and that supports their hypothesis. They do some controls to make sure that if they're looking at fragments, what if we chop the image up? Will we still find faces? And the answer is no, because each algorithm looks at a range of types, so it doesn't just look at intermediate or small sizes, but it also looks at the larger sizes. It just assigns a smaller weight to them. So as the fragments increase of the image, the relative response also decreases. And so the actual title of their paper is Visual Features of Intermediate Complexity and Their Use in Classification. And now you have an understanding of why they labeled that their title. And that's about it. Some of it addresses biological implications. So the paper said this model suggests if cortical cells are tested, the response of some units with large receptive fields will saturate at intermediate rather than full resolution, and this is not yet proven. And then my question is this just a variation of principal component analysis? Because it just uses fragments instead of a whole picture, but it still relies on this concept of principal components and, like Udi said, building blocks. But because our face or our human brain and other brains are not linear, do we really have these building blocks? Or do we do some sort of more complicated parallel processing that doesn't require building blocks? And this is a question that I think hasn't really been addressed in the visual literature as of yet. Specifically, what about concepts of abstraction? So for example, a smiley face doesn't really look like a face at all that much, but when we see one, we know it's a face. So at what point are we able to see smiley faces or concept cells, as people mentioned? So how does that interweave and connect? And my hypothesis is that these concept cells actually arrive earlier in the stream than we think it does. So I don't think it goes from V1 to V4 to TO, TI. I think at a very early stage it probably branches out into the concept stages right away. But that's a hypothesis that I personally have. So, and then what do hierarchies of classification? So yeah, it goes along the question of when do these hierarchies of classification interact? For example, if I see Udi, I might not think face first. I might just think, oh, it's Udi. And so at what point do all these representations overlap, and which one becomes the priority? So how do the hierarchies start to dissociate themselves. And my conjecture is that these hierarchies are dynamic. I think the more you know a subject, the more specific it becomes in your mind. And this is also stuff that hasn't really been studied biologically. And then these are some questions that came from lecture with Shaul and Udi, and these are, well, can computers learn this classification method? I mean, we as humans just learn it naturally, but how can a computer do that without us inputting an algorithm? And how much of today's progress is attributed to algorithm versus just faster computing and matching? And that's it.
Questions from you first, and then.
Sure.
How were the fragments decided, chosen?
They were also done in a randomized trial basis, so I think they stepped it up in 3 pixels, 3 pixels, 3 pixels.
Okay, and the intermediate ones were composed from the small ones?
Yes, each intermediate pixel is composed of a smaller segment. So it's they say it's a nested. Where is this? Right here. So it's you can see here it's nested fragments, and even these smaller fragments have more.
Oh, but I think here's a very important point. I think that the intermediate level, they just make, they take a picture and they generate, I don't know how many thousands of these possible intermediate level fragments. The point is that you can use the same technique that they've mentioned, using information theory, and apply it to the intermediate level again. Okay? So that's the idea, I think, of the sort of hierarchy. So if this would correspond to, say, V4, maybe this would correspond more to V2 like, okay? So this is a technique which is not just limited to getting that sort of representation, but you build up on it to build the whole hierarchy. So that's, I think, a major feature of this technique. But the question is, how biologically plausible is it? First of all,
right, you're saying that eventually if you keep taking sub-images, you'll get receptive fields and
presumably
edges,
you're going to get to V1,
edges.
okay?
Right,
I mean,
exactly.
this is already getting there, okay? But and
yeah.
but you can apply the same technique at different levels. That's a very important feature.
Right.
Worth mentioning.
And sorry, let me add to that. So they do specify, I think images are less than 4% of the actual face size for small, and large is greater than 33% of the face size for, so they have this threshold that they set. That was part of your question.
But how from the threshold it's randomly chosen?
Yes. They mentioned they chose the threshold that gave them maximum merit information after they calculated this. So it's an iterative process. They didn't just get this formula and do it. They went back, okay, we have more information here, went back, changed the threshold, went back. Yeah, it was an iterative process.
In a number of ways. Another is in the issue of which is the best fragment.
Right.
So once they compute, what's the information obtained from this fragment, the drop or the sort of mutual information, they take that into consideration to compute the next one. Okay, so now the left entropy or the left unknown information, okay, is the original one minus that one.
Right.
Okay, and then
added to the Gadi and then Dan.
Right. So two sub-questions. Was there a difference? Did they show like random faces or faces that were known of like celebrities or people they know?
So this is all for computers. So it wasn't done on humans. It's just an algorithm.
Right. Okay.
So in that sense, I believe they were all male, white.
Right.
If you noticed, I tried to put in some cultural diversity in my
But the question is how cluttered the scene is. Is this from profile or is this?
So it's all face front.
Right.
The training sets were all masked. If you look at the training sets, here, if you look at the training sets, they're all masked faces. But once you look at the images they processed, so here, they were embedded in a scene. So, and the face wasn't always in the center. It was around, and sometimes there were more faces.
Yeah, and was there a difference between if the segment was from the eye area or from nose and mouth area?
So
Like,
they
is
had.
it easier to distinguish an eye rather than a nose, or?
Yes, so I think your question relates to which segment gives the most information. So yeah,
Okay.
these are the main 8 segments that give the most information. So you can see there's eye. This one is the hairline. I thought that was very surprising because you don't usually think of the hairline as a, you know. And then this one is kind of the nose area,
Yeah.
and that one's a bigger blow up of the eyes and nose. So it looks like the eye plays a very important role, and then later on, having a nose and a mouth is important.
Okay,
So,
one last question.
yeah.
It's done. So,
That was what I wanted to ask about, because
Oh,
when you scan a face,
yeah.
you can see that people usually look at the eye area and also the mouth.
Mhm.
And what we show in this experiment is that the eye fragment is the most important, right?
Mhm. Yeah.
it's not just the eye. It's not an isolated eye. It's an eye with a nose, as you've seen. So there
Yeah,
is
but
really a
that
side.
fragment is only no, also visible.
Okay, but
Right.
so it's obviously not just the eye itself, but it's sort of the intermediate level.
But it correlates with the scanning of the picture. And
I don't think it's correlated with that. No,
so
no, no.
so
But remember, these are building blocks to have a representation that you can recognize as a face in the image. That's all you're asking for. Okay, I'm not sure that should be related in any way to the scanning. The fact that eyes are the most important, what you're suggesting is, okay, the eyes are most important in the scanning,
but when you
should
scan,
reflect, the scanning procedure should reflect
yeah, because
those.
when you scan again and again, you have more fragments of
That is
the
right for
area.
one reason, that if you fixate on a specific point, that is, you have the highest resolution in that area. So if you fixate on the eye, that's the highest resolution, and if you fixate at a different position, then it's not as then the resolution drops considerably. Okay, but I think we
Thank you.
should
Yeah.
switch now, done. So okay, let's take 5 minutes break so that you can sort of prepare everything. And since we're running out of time, it will be only 5 minutes.
Okay. Yeah. So we'll just. Oh, sure. I brought ice. And with the water. Okay.
First of all, it's a classification. Basically, they try to separate the intermediate and small in the light. Vogliono mano, loro in mano, loro. Ya se quita la fine.
Yeah, that was on the top.
That's fun, yeah. Like, okay, so we just did this, we ignored these matrices and have 7,000 features in a training set of 12, and this shows why you have amazing accuracy and such like it's then for these type of things actually needs to be
יש דרך עושה שנראה תמונה?
and basically how do you know that another thing is basically a technique that takes specific light. It's enough. How we build up the features. When I build up the features, basically write it down in the web, how many counts of features you will have, just what represents and how do you build it up. This is the thing is very big, but you could actually apply PCA or LDA to that again. Looking at deep sequences.
خلي ما في فوق شرط مفيها اللي فوق لا تشبه فيها لما كرين
זה לא מופיע פה, זה לא...
הנה זה פה אתה רואה? תשבه فيها למה كرين חיברתי אותו אני תשבه فيها למה كرين שלא חיברתי את זה נכון למחשב יכול להיות אבל אם אני רוצה לחבר על המקרן
Basically, PCA is finding which combination.
Really?
no laptop. She just
It was connected.
לא, אבל הבנתי.
Wait, what? Oh, because I used Udi's laptop.
And what way was it?
Oh, so it's connected. So you just need to change the setting on your computer to laptop and projection, right?
No, but it projects to this computer.
Um,
Okay.
שי, את יכולה פשוט שתכין לי קפה שחור? את יכולה להכין לי קפה שחור בבקשה?
גם?
לא. נו.
זהו,
לא.
I have another question that if you want to interrupt him.
טוב, שנייה.
I was wondering if they talk about the moral segments that compose the
אתם לא רוצים פשוט להעביר את זה למחשב הזה?
they search for the moral
איך אני
segments
מעביר?
that are common
פשוט
to
עם דיסק און
most
קי.
of the intermediate
אה?
segments.
עם דיסק און קי
that
פשוט.
will. Oh, that would copy
להביא את
that.
הדיסק און קי
No,
שלי?
they didn't do that.
לא יודע, הם לא מצליחים להריץ לי את זה.
זה מופיע פה, אתה רואה?
It can make the complex fields
כשחיברתי את
החיבור?
המחשב, כן.
זה החיבור, כן.
כשחיברתי את
They
המחשב,
probably
הוא
something
מופיע
like
פה
I,
ולא על המקרן.
a smaller segment of each of the intermediate segments,
מוזר,
right?
אז בוא
So
נעשה
maybe
קשה.
maybe a cell is just the eye and it's like intertwined with other cells. Yeah,
אז כאילו יש לו פה תמונה שהיא נראית לא... מה?
שלי, תמונה שלי.
לא, אבל זה לא מה שהמסך
It
שלך
was an
עכשיו בכלל.
interesting concept.
לא,
לא, אבל יש לי
כי הוא
שני...
מפריד, כן, הוא מפריד את המסכים כאילו.
אתה רוצה שאני אביא את ה-USB?
כן, נראה לי.
זה הכי פשוט, כן. אפשר, אתה יודע, כאילו...
פשוט נשים את זה על המחשב הזה וזהו.
מה?
עכשיו פשוט נשים את זה על המחשב הזה.
אתה יכול לשים שם
אתה
גם
יכול לשים את זה גם.
מוזר מאוד, כאילו, כן,
יאללה,
תנסה לנתק את זה שוב, אתה יודע, מאיזושהי סיבה לא חיברת פה, אבל זה גם מחשבות פה.
Right. Yeah. Wikipedia is helpful for that.
אז תביא את הפוינטר שלך, דן.
זה מופיע מה שיש
היינו.
פה, אני יודע, ומה שיש פה מופיע פה, ולא על המקרן. זאת הבעיה.
הוא חיבר עכשיו המצגת שלי פשוט.
שים את זה על המחשב הזה.
כן.
הכי פשוט, כן, בוא, כאילו, חבל הזמן שלנו.
תן לי, אני נותק אותך ואני רוצה להקליק את שלי גם, כי אחרת לא יהיה לנו זמן באמצע עכשיו להתחיל לשחק עם זה.
טוב, אז זה בכל מקרה תחבר לשם.
Basically, when he invented field, he also diffused the tables and he basically covered most of the field. Yeah. It's something you can apply to a lot of stuff.
סליחה, איך אומרים? הזמן קצר, זה נכון.
כן, יש לי שיעור אחד.
וגם התחלנו מאוחר. בסדר, לא תספיק הכל, זה לא נראה לי קריטי, אבל לא, באמת, הכי קריטי
זה לא משנה מה שהוא אם הוא לא יספיק, אבל אני אכנס לזמן, יהיה לי רק רבע שעה במקום ספק.
נכון.
ואז זה לא בסדר.
נכון.
אז הוא חייב לסיים עד ברבע. זאת אומרת, יש לו, עכשיו יש לו חצי שעה. אני מצטער.
בסדר, לא נורא. באמת, לא, בסדר. מה שחשוב שמה שנעביר
וואי, הוא ממש שיטים, אני לא מבין מה קורה איתו. נו, הוא לא זה, הוא לא זז. מה קורה?
זה מוזר, כי המחשב שלי הכל היה בסדר, אז אין בעיה פה עם המערכת. זה משהו מהחיבור שלך, יכול להיות שזה... אבל להעתיק הכי כדאי, כי בוא נחסוך את ה...
אולי תעתיק את זה אחר כך בצד גם, שלא יתחיל גם.
שנייה אחת, זהו.
אתה מוכן עם המצגת שלך על המחשב הגדול או חזאי?
זה פה על ה-USB, זה פה על המחשב שלו, המצגת שלי.
זהו.
בסדר, בוא, הנה, יאללה.
אתה יכול להתחיל.
בוא נשים את זה...
תשאיר לי את ה...
אתה יודע איך להשתמש בו?
אמרתי לו שלשום.
אוקיי.
נראה לי כבוי.
But I actually this
למעלה בעצם אתה... להעתיק לך אותו ל...
אתה יכול לפתוח ישר מהמצגת, מה-USB כאילו.
כן, אבל זה לוקח יותר זמן אחר כך. אתה רוצה לעבור וזה, כאילו זה ה... אבל קדימה, אלה. אני קורא לכולם פנימה, בסדר חגי?
דן? כן, כן, לא, אבל מעביר לך? כן. אני לא רוצה לעשות לך ספוילר. Okay, so I'll start. So hi everyone, I'm going to talk about visual object recognition. So briefly I'm going to give you a slight review from an article and then a bit more research from another article. So the first one is a review from DiCarlo from MIT. So like a big question, how does the brain solve visual object recognition? So first of all, why is it interesting? What's the phenomenon we're seeing? So we kind of effortlessly detect and classify objects from on like tens of thousands of possibilities and do it very quickly within just a fraction of a second. That is despite tremendous variation in the appearance of each object. Okay, so the big question is like how? How do we do it? So it's not a very good defined question. And so what does it really mean that you want to say, we want to understand object recognition? So actually, there's not a real agreement about what a sufficient answer to this question might be. So there's more like the theoretical approach, which they're saying would be the ability to construct an artificial system that would do it just as well as us. And there's more the experimental approach, which said that we should map the spatial layout and connectivity, the relevant brain areas, and reaching all the exact cell and molecular target that can be used, predicting molecular. So, but there's no a real agreement. Okay, so and now with this problem we have like a very big challenge in both of the approaches, and you all heard of it, I think, with this lecture, and this is the invariance problem. So if let's say I hold this marker here, so there is a specific stimuli on your retina right now, and you will say, okay, it's a red marker. And if I will move it somewhere around the class and rotate it and with different illumination, so you all have totally different stimuli in your retinas, but you'll still, within the same fraction of a second, will say, okay, it's the same object. So there's lots of invariances. There's the one position and one related to the scale, to the orientation, the illumination, and even the context. Same objects could appear in different contexts. And the big question is, how does the system solve it? There's also like a categorization problem, which you say, okay, this is a marker, but also this one is a marker, despite they're different. But I won't address this question right now. So this is basically like the question. So you can see here, you can say very fast that these all images, you call them car, despite they have different orientation, illumination, context, and these all are not cars. And now it's very simple because it's all black and white. There's no color here at all. So you have like, I call it like a set of initial conditions, physical stimuli, and they all like converging to the same solution, they're all the same object. Okay, so where is the magic happening? Udi already showed us our slide. It's happening, we heard about the pathway, but briefly. And once the information gets to V1, we heard about the ventral and the dorsal pathway. So it is believed to be happening to the ventral visual pathway, which is through here. And later on, we'll see what happens to the information over there. So it's believed to be from V1 to V4 to the IT neurons right here, and they are. It is believed that they are like control the object recognition problem. The dorsal one is more about where and what. Okay, so let's get some graphic intuition before we go on the. We need some tools if we want to address this problem. So we will imagine the responses, and our responses are in final rate. Let's say we have populations of neurons. So we'll address the responses of n neurons to a particular image as some response vectors with dimensionality of n, which is the numbers of neurons. And we'll define it will soon be much clearer in the next slide. And we'll define a low dimensional surface in this high n dimensional space, which we call it an object identity manifold. And it is believed that the ventral visual pathway, okay, that this pathway, it's kind of untangles the information triangles like sabuch, so it makes it, so the information was very tangled at the beginning, and later it is believed that it's very untangled, so the system can separate objects. Okay, so this is what I meant. So, okay, we have here a response at spikes per second of some populations of n neurons to some objects, okay? So this is like an n-dimensional response vector, okay? And this is, for example, some identity preserving transformation, okay? It's the same object and you get slightly different results. And this is for a different image. And we can map, okay, each one of these objects, we can map them into like responses into like an n-dimensional space, okay? So ignore this R3, R4 because they should be all linearly independent. But this is just an illustration like in 3D, okay? So we assume that each vector we can map it into this space, okay? And now it is believed that neurons at the early stages, these manifolds are very curved, and the corresponding to different objects will be very tangled together. And later on, each object manifold will be less curved, and the manifold will be more flat and separate, more untangled. Okay, what do I mean? I mean, so this is what believed to be happening. At the beginning, it was, so imagine it's an n-dimensional, it's not just 3. So this is responses, let's say, for 3 cars, and this is for 3 airplanes. It's believed that this is what's unknown. It's a very big problem also in computer science and machine learning. That is later on it's more untangled and we can discriminate much easier between objects.
Let's
Okay?
just make one thing clear here when we're talking about the responses. Just to make it clear, for a two-dimensional case, I'll stop you for 1 minute just to make sure that we didn't lose anyone. This means that neuron 1 fires at that level of response, and neuron 2 fires at that level of response, and so on and so forth. So these are all for one image, for one type of image, and this is for another.
Okay, so it's the same transformation. So it's the same information at the beginning. It goes from pure transformation until the IT is believed to reach like this state, which is we can declare, we can recognize objects. Okay, so object recognition is like the ability to separate images that contain one particular object from images that do not. So in our case, it will be positioning a decision boundary. I have a hyperplane to separate. I will soon explain what I mean. A hyperplane to separate the manifold. All right. So what's a hyperplane? A hyperplane basically is if we have an n-dimension space. So a hyperplane is an n minus 1. It's like a subspace. So the method they use for data analysis in the paper I'll soon show you, they use a lot of linear classifier, which is a big thing in machine learning. What does it do? Basically, it classifies between 2 groups. So let's say these are all like yes answers, these are all no answers, for example, and now we're looking only like a 2-dimensional space. So a hyperplane in this case will be n minus 1, so it will be a line. So these are all like examples for classifiers. So you can see that A3 is not a classifier at all because it doesn't really classify between the 2 groups. Now H1 and H2 are both classified, but there's some algorithm to make it optimal. So I guess you can assume that H2 is better because distance is the maximum of the nearest most neighbor is going to maximum. And how do you make such a classifier? So basically, you need to collect a lot of data. And then when you think you have sufficient data, So you use these machine learning techniques and put your classifier, okay, such that it works. And from this point on, every data you will collect, you will test it according to the same classifier you built. So from now on, I can test whether new information will be if it was a black dot and it would be on this side of the classifier, it would be a correct, similar to what Lily showed. It could be false negative, false positive, correct, or two corrects, right? And so this is an example in 2D, and we can also illustrate in 3D, but in higher so in 3D it would be a plane, it's not a line. But in higher dimensions it will be also subspaces, so we cannot draw them. Okay, now maybe it's sufficient tools to go inside the next article of the same Di Carlo from MIT, where they were showing that the selectivity and tolerance is a different word for invariance. They were claiming that they both increase as the visual information propagates from cortical V4 to IT. Okay, so remember the hierarchy? So now they will try to show and quantify how does these two properties increase. Okay, so what did they do? Basically, very briefly, they took two macaque. I'll soon show the exact setup, but they took two macaque monkeys, and we want to build classifiers, so we need to collect a lot of data. So they were recording from the V4 and from their IT neurons while they were watching images. Okay. Very in the beginning, they found what Udi showed us last lecture about. So I'll go very briefly about changes in receptive fields. So in V4, they saw the nice contrast between the mid of the receptive field and how the side changes, how they're in phase. So Udi already showed us. Maybe later we'll see how does it, what's important about that. So this is the experiment setup. So the monkey, while he was being recorded, both from IT and V4, he should fixate at a point, and he was seeing images, okay? Until he was seeing this motorcycle image. When he saw this motorcycle image, he should have do a fast decay down to get it to. So okay, there's nothing special of this motorcycle image. It could be any other image, but just making the monkey looking at the images because it is his chance to get a reward. Okay. So and they're all like black and white, so it's simpler, and they were all shown in sequence in random order for 200 milliseconds. Okay. Can someone tell me what object does he see here?
Surface of the moon.
Okay.
No?
So actually it's nothing, and you shouldn't see here any object, because this was kind of the heart of their experiment, because this is what they call the scrambled image, and this is what they call natural image. Okay. Scrambled images are not any object you should recognize. How did they make them? So it's very, it's also very difficult to make them. Or briefly, they were looking at some statistical measurement of the mean. It's a lot in vision and image processing, which I don't understand very much. But briefly, they were looking at the mean, the variance skewness of the images, and they were putting them to some Gaussian white noise and producing these scrambled images. Okay, and what's important is that all the local features were kept at the same ratio in the scrambled images. Just there's no such an object here. Okay, and they did that for 50 images. So they had a series of 50 natural images and 50 scrambled images. Okay, for each one. And they were shown to the two macaque monkeys, and recording was taken, and they wrote the spike rate per second. Okay, so the thing is, these scrambled images are not any known object that the system can recognize. Okay, and now a bit about response clouds. Okay, so as before, they were collecting data. So this is, for example, a response vector. This is here a list of neurons, and more the black is bar, as more the bar is black, so the spike rate was lower. Okay, you can see white is a lot of spikes within the same 200 millisecond window. So they were showing images, and they were mapping them into this n-dimensional space. Okay, and after they collected sufficient data, they put their classifiers, and from this point on, they could check whether for new images whether they would have correct or wrong answers. Okay, this is. So, and why do we get response clouds? Because we can let the monkey see this image A, but because the neurons line up, are believed to be noise and everything, so
each time we get a little bit different point, and that produces these clouds. They call them,
For a given image.
yeah, for a given image. So these all correspond to A, these to B, and so on and so forth. And the ability of the population to discriminate between the images is proportional to how far apart these response clouds are in this n-dimensional space. Okay? So what they did next, this is how they built their linear classifiers. Now it's presented as a line, though it was in a higher dimension. And they could check whether it was correct or wrong answer next. Okay?
They didn't use any image categories, but image by image classification.
Yeah, so they had 50 images natural and 50 scrambled.
Okay.
And they built accordingly. They used first only the natural images. Okay, the natural images were used to build the classifiers, and then they were checking on all the rest of the images, natural and scrambled. Okay.
And this is built from the activity in IT cortex, or is it also for V1, or did they build two different classifiers?
Yeah, so for each population, they built
okay.
their own classifier. This is like in general.
Okay.
Okay? So what was their hypothesis? So this is the ventral visual pathway as long as we move forward. So let's assume like V4 is somewhere here and IT is somewhere here. And this performance was measured as the percentage correct on that image identification. It was like a simulation of the computer to see whether they get a correct or wrong answer. Okay? So the hypothesis was for natural images, the performance, and for natural and scrambled images, the performance of the V4 neurons will be quite the same. It will look something like that. The response clouds are
In V1. The point is that in V1, the neurons respond just as much to scrambled images as they respond to the natural images.
Yeah.
Because they have the same features, local features.
Exactly. Okay.
V1
V4 is somewhere here. Okay. And in the IT neurons, they can't recognize the scrambled objects, so it results in the collapsing of all the clouds towards the origin. Okay. So that was their hypothesis, and this is the results. What they get. Okay. So what can we see? We can see the percentage correct, the performance versus the numbers of neurons. Okay, so they were looking, so as you can see, there's no much difference for V4. So black is natural images and red is the scrambled images, and there's no much difference for V4 neurons, but for IT there's a big difference. Okay? As you look for, and this is for an exact number of 140 neurons, just taking here these 2 points and these 2 points, and you can see what happens with V4, the big fault. Okay? And exactly the same, this is exactly the same two figures, but we look on, just to get better reference, but we look at the specific performance level. Like here it was 140 neurons, here it was 121, and compare them just to get better reference, to get this line flat as a reference. Now look at this graph E, and now look at their hypothesis one. Now, you should be amazed. Very nice, it's the same. So this is what they found out about selectivity and what happens along the pathway. Okay? So they did some control to use, they thought maybe their linear readout is going to, they got it because how they built the classifier and everything, so they did another 2 techniques and they got consistent results, and did it also with very short time windows and they got consistent results. So to conclude regarding selectivity, what can they say? They can say that neurons at lower level of visual processing can encode more local structure, where neurons at higher stage of visual system becomes more sensitive to specific conjunction of this local feature. Okay? And that neurons in IT do not merely encode any arbitrary configuration of local structure. Rather, they are very tuned to a particular configuration found only in the natural image. Okay, so that was regarding selectivity. Now, what about the invariance I spoke at the beginning? They were addressing now this question, so forget all these scrambled images. Okay, I have 5 minutes, right? 10 minutes. Okay, so now they were addressing the invariance terms, so forget the scrambled images. What they did is this kind of setup. So they had the object, and there were just 3 changes. So the changes either in scale or in position or putting in different contents, and they had 10 of this sets. Okay. So what they were doing, they were again recording by showing the images, and then it's some images were changes in position, scale, or context. Okay. So in order to compare something, you need a reference, like just before you compared between the marker here and over there with different orientation and illumination. So we need to get some reference. So the arbitrary chose this one to be the reference one, and that was their hypothesis.
the pathway, your generalization performance would be higher. Okay, so if it was the reference, so neurons, so if I now change an object, so neurons here at V4 will perform much less. Okay, where the neurons in the IT will perform almost the same, and this is how it's the corresponding what happens to the response cloud, how they cluster in a classifier, and here for IT they won't pass it. Okay, and what were their results? Again, they were looking at number of neurons, and they saw that for neurons in IT, almost the performance didn't change dramatically. And again, they get this graph, and we can get it again. This black one. The black is the reference, and this is just for the position one. Okay, this is just for the changing the position, and they can play again and look only for a specific performance and get the same graph as a hypothesis. Okay, and this is the results for all of the conditions. So what do we see? We see the capacity. The capacity is basically the blue line divided by the black line. Okay, so if you're perfect at generalization, you get one capacity. If you're very bad, you'll get 0. And you can see how IT neurons, in all of the tests they did, they had better generalization capacity. Okay, maybe in this scale of half or 1.5, they were almost the same, but when you change the scale a bit more, you can see the difference. Okay, so what was and again they did 2 more controls. I won't go into it, but I don't have time. But they had consistent results, and they did also in different time windows. And this is the result they got also for training. Okay, so they were training also on all of the conditions. So they thought maybe because we trained only on the reference, so we got this result. So they were doing on the conditions and testing again. They got consistent results. So to conclude, what they had regarding invariance, so the format of the IT representation is superior to V4 with regard to invariant object identification in terms of linear separability and generalization. And this is not due to any lack of information in V4, right? The same information is just being from various transformations that formed it. Okay? The next thing, I'm not showing it. They were addressing the single unit properties. What's the single unit for selectivity? What produces the selectivity, and what's the tolerance? But Udi here is angry.
Intolerant.
Yeah, so we don't have time, so I'll skip it. So just some criticism is there's many other inputs to. We saw the difference between V4 and IT neurons regarding selectivity and invariance. And what about memory effect? There's many other inputs to the systems, or is there any meaning to the interspike interval? Just the number of spikes matters. That is the only thing that's being coded. And the big thing is that they were assuming the linears will find you independently. So, but actually they're all connected in the network. This is why they put them into such a vector in the space. So I don't know if it's legit. And why even use this linear classifier? Why not use something like that? Okay. Though, as far as I read, just for big computation with big dimensions, linear classifier work much faster. Maybe that was the reason, but I don't know. So this is kind of it. Thank you for listening to me.
We want to discuss in a few words the issues raised here. Just a few things. I think this issue is really a critical one because, I mean, what they've done is taken the firing rate of n neurons, say n being 100 neurons, okay, and generate a vector from that. And you're looking at this on a trial-by-trial basis, right? So you're taking most of the data for your training, and then you're trying it out on the 10% of the data that you've left out on a testing phase and seeing, okay, can you actually, in a testing phase, correctly classify the stimulus, okay? Now, if the neurons are correlated on a trial-by-trial basis, as we know they are, then they fluctuate together, right? And if they fluctuate together, that may have a dramatic effect on your ability to decipher the information. So that's one major issue here, I think, which is you're absolutely right that the right way to do it is what to do is to record these neurons in parallel. 100 neurons in parallel, then you see the actual activation on a trial-by-trial basis across all these neurons. While if you do this one at a time, then that's a problem. Okay? So that's the first issue. There's many other issues, but I think that the nice thing about this, okay, how does it relate to what I mentioned initially? You have here a representation that's based on a sort of vector coding of n neurons. As you've seen, the bigger the n, what do you get?
Better performance.
You notice that it's a monotonic function. So as you're increasing the number of neurons, you get a better performance on your classifier. Okay? And here, you see this? It's sort of a monotonic performance. And the rest I will cut just because Dana is really urgently needs to speak. So there's a lot of interesting issues we won't have time to get into.
In the presentation, the amount of information that is
Okay,
allowed.
that's good. And now the next talk by Dan is going to be a comparison between species. So up to now we were hearing about single unit recordings, okay, and how can you read out the activation of a population of single neurons, right? And now what Dan will refer to is a comparison. Dan, you go.
Thank you. I'm going to speak for Dan. Sorry.
I have exactly 25 minutes.
Go ahead.
Good. I will talk about the matching categorical object representation in anterior temporal cortex of man and monkey. First of all, I would like to summarize what we learned in the last 2 weeks in terms of the visual pathway in man and compare it to the monkey. What we can see here, this is the brain of a human. The information comes from the retina to LGN and then to the early visual cortex, the V1. And then there are 2 pathways, the dorsal pathway that goes up and the ventral pathway that goes to V4 and then to the IT. IT, this is what I'm going to talk today and explain you what is going on there and why the categorical object representation is so important in our life and in monkey's life as well. So this is the brain of the monkey, and the information also goes from the retina through LGN to the early visual cortex, and then the same pathway, dorsal pathway, and the ventral pathway also goes to the IT. And now, what are the big questions that they are asking in this paper? The first question, do monkeys and humans see the world similarly? This is a bit philosophical question, and I'm not really sure that they are able to answer this question. So we will not try even to answer this question. The second question, do monkeys categorize objects as humans do? So this question also a bit vague, because how can I define monkeys categorize objects?
So the brains of monkeys categorize, right?
Right, but it's also how can I know that they are categorized objects? So this is the reason we will go to more specific questions. And the first specific question will be this one. Do human IT response patterns form category clusters as reported for monkey IT? Kiani in 2007, he did an electrophysiological experiment and he recorded from the inferior temporal cortex in a monkey, and he found that the IT response patterns form category clusters. And now the question is if the human have something similar to the monkeys. This is what we will address in this talk. The second question, does the human IT simply represent the visual appearance of objects? What does it mean, visual appearance? What I understand from this question is that in early visual cortex, it is a low-level features, and when it comes to the IT, then it's high-level features, and this is the reason the visual appearance of the object in IT. So then, if so, what is the categorical structure, and does it match between species? And now,
Is it just, I think the issue is visual appearance versus semantic or categorical appearance based on the fact that 2 objects could be semantically related, but not necessarily visually related.
right, right.
So that's a level that we have following language that, of course, primates don't have.
So, thank you. And now to the most interesting question. And what is the most interesting question? It's usually about the mechanism and how does it work? So this question is, how is the representation of the object transformed between the early visual cortex and the IT? Does anyone here have any idea how we can try and make an experiment, or how we can answer this kind of question?
Correlation of activity between the two areas.
Okay, good. Someone else?
Maybe it's a process of construction instead of transformation. Construct the representation.
Yes, it's also very good, but it's very hard and very challenging to make such experiment. So it's an open question, and it's basically one of the most interesting questions to do and to answer. So let's start with the overview of the experiment and analysis. They presented images of real-world objects to monkeys and humans. Then they measured the IQ response patterns, the single cell recording and fMRI. You see the difference? The monkey is a single cell recording, and for the humans it's fMRI. It's totally different method. Another question, can we compare? Is it correct to compare? And why there is a reason to compare between both of them? So, and then they studied similarity of object representation while they were focusing on paratemporal cortex. And this is one of the most important, because here they compared the representation of human and monkey IT, and they developed this technique of representational similarity matrices. So let's go to the core concept. What does it mean, the similarity matrix? Core concept, representation similarity matrix. We will look at something very basic, and then we will go to more complicated images and matrices. We show two images to the subject, and then we get some activity pattern, as we saw in this lecture. And to each one of the images, we have some the firing rate in case of the monkey, and in case of the human, it will be voxel number. And we do the correlation. But what they're doing, they're not doing just the correlation. They're doing y minus the correlation. And we'll see why it might be important in this case. So and then this is how we find each one of the cells. So what we can see here, that the blue, the correlation is high, and the red, the correlation is low. And now let's go to the brain activity measurement that they did. The monkey, they just took the data from someone else, and then they compared to the human. In a monkey, we had the single cell recording in 2 monkeys with total 674 cells. In human, they did fMRI and 316 voxels. So now let's go to the experiment.
So that's the size of the vector n, right?
Yes, this is the size, right?
Of 2 vectors.
2 vectors. So let's go to the experiment. They showed 92 stimulus experiments with the animate and inanimate. There are faces here, body parts, and faces of the animals, as well as natural and artificial images. Now, let's see how the matrix will look like for 92 images. So let's say we have 2 here, and we have another 2 here. And then the brain has some activity, and the activity pattern, also we can do the correlation the same way, and this is how we find this one cell in the 92 by 92 matrix. So this is how it looks like, the similarity matrix. There are images here of faces and faces of the animals, as well as on the other side, and when they compute these dissimilarity matrices of the human inferior temporal cortex, there is this one nice cluster. What does it mean? That there is a correlation between the human face number 1 and number 2 and the rest. But also we can see some correlation between the faces of the animals and the faces of the humans. So maybe humans see faces of animals, and humans very, very similar. And there is high correlation, at least on the fMRI. And also there is another category between the animate and inanimate. So now we saw what's happening in the human brain. Let's see what's happening in the monkey brain when they're doing electrophysiological experiment. And here it looks very similar. So the clusters are also the same, and they also respond with the same technique, with the same correlation. And and there are also clusters here between between the faces of the animals and the face of the human here. So this is now we can really compare those two matrices, and the reason why, because now we compare the correlation and not the firing rate and fMRI. And we can see here a striking match between those two matrices. When we should keep in mind that those completely two different methods. One is fMRI for the humans, and the second one is single cell recording. And this is, one second, and this is their contribution to the science, where they really found the method to really show two different methods and compare them after some analysis and some computation.
Is it impossible to do fMRI for monkeys? I mean, why not do the same method for both?
So this is a very good question. Because first of all, we can do electrophysiology, and it's much more accurate considered in terms of the calculating each single neuron and looking at the firing rate than fMRI from one point of view. But maybe we can add to
I think it's
what.
But if your question is comparing humans and monkeys, you want to do the same method. It doesn't matter that electrophysiology is more accurate.
I think you're absolutely right. There's two issues here. There's a difference in scale or magnitude of the technique, where fMRI, as I said, you're averaging across 1 million neurons, and another a difference of species. So an intermediate step would be to compare fMRI in the monkey with a single unit recording in the monkey. They don't have that, but that would be wonderful if we had that capability.
But it's possible to do that. There are labs that
Yes, it is
can
possible to do that. They don't have it in their paper, but it's absolutely, yeah. fMRI monkeys are regularly now. But you have to use the same images. It's possible. It's not trivial, but it's possible to do.
So now we have this high dimension, as we heard from Hagai. Now we like to represent this in a 2 dimension. So what they're doing, they would like to visualize the representation. So let's arrange the images in a figure reflecting response pattern similarity. Images that are close together will be similar response pattern. It will represent similar response patterns, and the images that are far will represent dissimilar response patterns. And this is the multidimensional scaling. Edelman in 1998, he actually pioneered this method of application to fMRI. So this is the multidimensional scaling of human AT. This figure shows the unsupervised arrangement of the stimuli, of the image, of the reflecting or response pattern that we were able to record of fMRI in this case. And we can see that the faces are nearby, but also the faces of the animals are not very far from them.
So I just want to, I'm stopping you because you're doing great, but I want to keep everyone in line here. So when we talk about multidimensional scaling, we mentioned response patterns. So we have an n-dimensional vector of response, either the bold signal or the signal units, okay? And you get, as Dan said, you get these different responses for different objects here. So for the banana and for the scissors or for the snake, okay? And now you want, and these would map into point in this n-dimensional space. And you want to collapse this into something that we'd be able to see. That's what the MDS, multidimensional scaling, does for you. Of course, it involves some warping, but if you do, this is the best you can do in terms of a representation in 2 dimensions. And that's that is the outcome. So it's not exact in the sense that you've made some warping, but you do get a picture of what is similar to another in terms of the representation. That's the point. Sorry, Dan.
And now we can just put a black or red dot. Let's see what we will get. So this will be the animate, and this will be for the inanimate. And this is what it looks like when we reduce from the high dimensional space to the 2-dimensional space. We can see 2 categories separated really well. And
as we see in the left.
yes, but here this is hard to see it in a 2-dimension in a nice representation like this. What we can see here. Here
it's very easy to see. There's a blue color and the red one, right? So
it's nice
the cross scale, you see the division between the animate and the inanimate.
Why?
What about
Why
yeah,
does
that's
it
okay.
Mix.
Because
through
categories
the
are
mix?
not represented nicely there.
Why? What's the reason the category is not represented there?
Because it's very local.
Very good. Local and it's low level features. This is what we discussed during the last 2 weeks, that in early visual cortex, probably it's because of the color and shape that is represented in early visual cortex. This is how it looks like. There is no categorical representation here, almost at all. And there is just one cloud. It's impossible to separate between both of them. It's really bad, right? So, and now we can really compare between both of them, and we can see also the body basis and the natural lens, which are also very good match here. And we can do another methods of hierarchical clustering, and we can see also here all the image, and this is the one minus the correlation. And it's another method to represent the data. So let's go to the summary. Natural categorical structure in primatity, top level distinction, animate and inanimate, and faces form a separate type cluster. But the man to monkey match of IT, representational similarity match in major categorical clusters. This is what we really talked during the last 15 minutes. Interpretation, human and monkey IT. Monkey IT may host a common code for categorical object representation. This is the take-home message. And I'd like to show you some of the subsequent work that has been done in Germany in the laboratory for now, it's for patients with neurosurgical patients that were recorded in a single cell recording, and they use the same method in amygdala. And the beautiful thing here that we can see there is some correlation only in the right amygdala, but not on the left amygdala. And what it can show to us, if we present the animals images, and there is only just an interesting image to the right amygdala, there is a response of the firing rate. What they claim, it may reflect the importance that animals had for our evolutionary path. So now to some of the critics that I personally have. Maybe you will not like some of them. So did they really answer the questions? Do human AT response patterns form category clusters as monkey AT? Well, yes, according to their method, this is correct. But the question is, can I really compare fMRI representation, which each voxel has more than 1 million neurons, to single cell recording? It's a hard question. If they are just looking at the correlation, so it's true. But I don't know if in other cases it will be correct. If I will just record from a single cell recording, it will be the same result. The second question, does IT simply represent the visual appearance of objects? Well, they're not really answering this question almost at all. The third question is probably the most challenging, and they're not even trying to answer this question. So what we learned from this paper, we learned that we can really take two different species and we are able to compare. And this is what their contribution to the science. But no one knows why this is important what they found. There is no really an interesting idea why, what's the concept? Okay, this is the categorical representation. What's the next stage? Why is it so important? This is my point of view. Thank you very much.
So we have time for a little general discussion, okay? And the first thing I want to address is the questions raised here, and I have a few others. The one thing, okay, this difference between monkeys, to some extent it looks like an amazing paper, right? You're taking two different techniques, one in which you're averaging the signals of, as we said, around 1 million neurons, building a vector from that response, which is just a correlate of neuronal activity. It's not neural activity, you're measuring both, right? And lo and behold, you get similar representations of objects, okay? And not only that, they're similar across species and across scale. So I think the point that was raised by Neil is absolutely right. If you want the intermediate step to understand if it's the scale that is conserved, okay, more important aspect here? Is it the change in terms of from one species to the other, or is it the change in the scale? And it looks like you can accommodate both, and you have no problem, which is, I think, really mind-boggling. Okay, and that's the first thing to think about. The other point I want to sort of stress is the comparison between the two last talks that we've heard, Haggai and Dan. They're addressing similar questions. So, for instance, it says, how is it transformed between early visual cortex and IT? That's exactly what Dan was referring to, what Haggai was referring to, right? That's exactly that. But these are two different sort of techniques which are somewhat complementary. Can we sort of understand what's the difference between these two techniques? What are we looking at in one versus the other? Haggai, Dan, can you refer to that? Because, I mean, what's common to both? You're taking the vector representation, right? Now, in Dan's case, Haggai's case, what you do is you're looking on a trial-by-trial basis, right? So we took, say, 90% of the trials to generate this sort of cluster here and a cluster there, and find the sort of the border between the two, and then test on the remaining 10% of the trials if they're within the two clusters or they're crossing the border, right? In Dan's case, we were looking at correlations between these vectors. And how do we compute these correlations? They're based on averages, okay? So you're looking at sort of an average response across many repetitions of the same stimulus, okay? Whether it is in the fMRI data or with single unit data, but they're averages, okay? So if you look at, let's go back and see the sort of the matrix. Okay, so this, okay, what is each entry here? Let's see that we got the picture here. Can someone sort of
One minus the correlation between the response vector to one specific non-animate phase,
right,
animate non-human phase, and I don't remember where you pointed it. Another.
Okay, okay. So these are again correlation between the two vectors, but on the between the average vectors. If you were to record the vectors on a trial-by-trial basis, there's noise, and therefore these vectors would change a bit. So there's another issue here, which Haggai referred to, and that is the trial-by-trial variation, which is lost here. Okay, so that's just a point to clarify to everyone. Let's go back to the questions you've raised and see if I've anything, or people have any. Okay, so okay. One last point that I want to make is, okay, they've looked at responses of neurons, right? What's the obvious thing to do, at least in humans? Behavior, right? That's what I do, okay? And we want to sort of correlate behavior with the neural responses. So right now, we've had, Don showed in one of these sort of picture of which images are closer to others in terms of their representation. Well, the first thing to ask is, okay, go to the humans and try to map these images and find here. Well, it seems, you know, if you look at this, okay, faces are clustered together, okay, fruits are clustered together. It all makes sense, okay, some sense to us. But in fact, actually, if you ask subjects about, okay, which image is, okay, how similar is this image and that image? He can give a number, right? And you can now get the, yeah, you can get a sort of a distance in terms of a similarity, in terms of the category of one image with another, and compare the two. Okay, and actually, Kriegskreuz has actually done that in later papers, and he finds that surprisingly, well, maybe not surprisingly, what would you expect? That different categories, I'm not giving you the answer, that's the level of semantics I was talking about. Okay, fruits, you join together as being fruits, even if visually they're very different from one another. Okay? And
Okay.
okay, you gotta
because you can show it here, I think, with the clustering better.
Okay, please. No, but that's the neuronal data.
Right.
You want a similar, you can do this exactly same thing with a behavioral data. And ask, okay, how do they correspond to one another? And that's a level that's not just here, but that's, you presume that the neuronal data reflect behavior, right? So you should see that correspondence as well. And this is something something which is somewhat troublesome. It's not quite the correspondence you expect. And the main thing in terms of behavior is that there's a further clustering of different categories. So the distance between one category, say the fruit, and another category, say the faces, is greater than it is here. Okay, so that's one other issue. What are the other questions that you asked? Maybe there's some questions that you want to raise. And you've also had some criticisms. So let's see then, what were your criticisms?
Sorry, but we have questions here.
Yeah. So that I think this is something that was addressed really by Hagai.
Yes.
Do you really think so? It says, how is the transformation representation transformed?
Well, what we've seen is that there's no, well.
So, and it only talks about what is the representation in one stage and what is the representation in the other stage. I don't think that the talk that Hagai gave mentioned anything about how this transformation actually is implemented.
I think what Hagai has shown is you take an image and you scramble it, okay, keeping the local features. He didn't describe exactly the algorithm, but it sounds very important. Keeping the local features to be the same, you find that in V1 it responds exactly the same. The vector representation is the same for the scrambled image as it is for the intact object. Okay? So, and as you move, if you remember his graph, as you move in the hierarchy, this difference becomes greater. Okay? Suggesting that you're generating an object of representation which was not evident in early visual cortex.
This doesn't tell anything about how this works, so that it doesn't explain the mechanism behind it.
Right. So the only sort of insight we have about mechanisms was actually from Lily's talk, in which we were talking about this nesting. Remember the hierarchy, that you can sort of generate a category of cells which are sensitive to faces from building blocks which are.
Nobody knows if in real brains this is similar to what Lily showed about.
You are absolutely right that, okay, the one thing is that theoreticians and people who actually do the recordings are not in common ground. So the next thing to do, if you were to take Shimon Uman's ideas seriously, is to go and check this and do the physiology to see if you actually can see that.
As Jan said, it's not that easy to do this mass parallel recordings that you would need for that.
That's right as well. But it's actually done, I mean, parallel recordings of, hundreds of cells are done nowadays. Tens of cells are done nowadays in many labs. So it is possible, but you have to sort of decide, this is what you want to do in life. Okay? Okay, any other questions, Lily? Yeah.
Oh, just, I'm wondering, has anyone looked at, in V1, if they did Hagai's experiment using the correlational study, but using very simple features in V1, so you would see the same correlation.
Wait, in Hagai's experiment, the data is there. You're asking, okay, can you now analyze it using the correlation method?
Yes,
Yeah,
in
they said
V1.
they did.
The data is there. So
They said they did some other techniques.
Okay.
They
And
used
did they
correlation and they got some results.
So they did the color graph thing, the edges, I mean, were.
yeah, I'm not sure what you're referring to, Lily. I'm sorry.
Okay, so in V1 it represents local features and edges, right?
Right.
So you're saying they also did the correlational study similar to what Dan's study showed, and then.
I don't know the exact
Right.
techniques they used, but they used
Okay.
two others, not based on this, the one that I showed.
And also previous Corte could do the classifier method of
Yeah, I mean, once you have the data, these are two methods of analysis. One focusing on the average response, and one focusing on a trial-by-trial variation. Okay? So, and both are valid and complementary.